Hey there, this is Mr. James. Just wanted to cover some basic digital media concepts. We're going to go over the first, at least, chunk of this today. I think we'll get enough in there to help you with these first couple um, assignments that we'll have. One of them for this week, I know, and we'll talk about how we're going to do that. But let's go ahead and do this. I'm going to share the screen and get my intro and orientation content area up here. Okay. If you have any questions about installing Adobe, I do want you to be able to do that. That is one of the assignments um, that we've had, and I want to make sure that that is something that you're able to get taken care of. Okay. Everybody should be enabled with your GGC email at this point. The help desk has confirmed that for me. If you have questions, check out this link right here in the intro and orientation section, how to install Adobe at home. Follow those instructions. And if you have trouble with that, let me know. We'll talk about it in class, or you can email me and I'll see what I can do to help out a little bit. Okay. All right. Okay. So let's look at basic digital media technology. This is the document. This is how I usually do this. It's usually the word guide or guidebook is in the document for each of these projects that I will post that gives you the content, the academic part of what we're doing. Usually, almost always, the criteria list for the project will be in there. And then there'll be sort of a short study guide for the test that we'll have for each of these, for most of these topics. Okay, so I'm going to click on this. This brings this up, and we'll try to make this so that we can see it all in here, most of it. Okay. So we're just going to do some basic digital media concepts. It's not, I'm not going to jump into raster images in Photoshop quite yet. Okay. So that will be our first big program that we'll work with. It'll be our first big project, and we'll talk specifically about that probably starting next week, maybe Thursday. But I do want to cover some of this that we've got coming up here. So let's just go ahead and start with the word data. Okay, so um, data, we as humans pretty much deal with data mostly in two ways. Okay, natural data and binary data. 100 years ago, 200 years ago, we mostly dealt with data just in the natural form. Okay, now we started to, maybe Morse code or the telegraph or something like that began to come up with some coded forms of data. In fact, there are a lot of coded forms of data. A language is a coded form of data, but a lot of what we deal with is either in natural data or binary data, and we'll talk about that just a bit. Natural data, a thermometer measures temperature. That kind of a thermometer that does that, that actually heats up a chemical inside of it, mercury, and causes that chemical to expand. That's natural data. Natural data is also called analog data. Okay, and it doesn't take a discrete form um, in ones and zeros or a set of steps. Okay, uh, it's usually in waves. So usually we're talking about something like, let me see if I can find. Here's some examples. Talking about something like light that a camera captures, or sound waves, light waves or sound waves that a microphone captures. Weight, the pull of gravity on how heavy an object is, temperature, pressure. Those kind of things are things that are measured chemically, mechanically in our natural world. And here's the thing about analog data: it's infinitely measurable. You can measure that in ever increasingly small steps or small measurements. Okay, if you measure 1 millionth of something, 1 millionth of a second of a sound wave, well, you could measure 2 millionths of a second, which is even smaller, of a sound wave. Okay, so that's infinite because the number system is infinite, and it can always get smaller. We're only limited by how small can we actually handle it. Okay. Once you get down that small, past a certain threshold, doesn't really matter. We've captured as much as our biological equipment, our eyes and ears and whatever else we use is able to detect. Okay. But analog data is in the form of waves. And what we do is use these devices, and they're engineered to do this, okay? Input devices are engineered to capture analog sound waves, light waves, whatever, and convert that into a discrete set of steps, binary data, ones and zeros, okay? Um, so as we're capturing this data, it is being converted into that set of ones and zeros. Ones and zeros corresponds to the circuitry inside of a computer made up of these tiny little circuits, billions and billions of circuits that really only acknowledge either being on or off. Okay, and even then it's not on or off, it's it's on or not as on because electricity does flow, a very low level, but it still flows. It has to flow through even those non-on, those considered off circuits so that it can continue to run. But it's detecting a certain level of electricity and it will infer whether that's either considered an on or a one or an off or a zero, which would be a zero. Okay. So all these ones and zeros are put together. We create numbers with that, the number system, the letter system, particularly on the keyboard. We're going to talk about that. We talk about other systems, the color model system. It's all made up of ones and zeros, and that is binary data. Okay, so I do want to talk about that just a sec and kind of make sure you can read this. It'd be a good idea to read this document. There's a couple websites here that you can, if you want to play around with creating circuits, you can online. Doing some kind of activities to check out the different types of circuits that programming languages are able to simulate and use to make decisions in the logic of a program. Okay, but we're not doing that. That's for those that is for those IT majors among us. Let's just get into this binary issue here. Okay, so these numbers right here in this binary code, there's 8 in what's considered a byte of data. Okay, bytes of data, that 8 bits has been sort of uh, set as a workable chunk of data. Okay, and we can it would allow for 256 options. Okay, in that set of 8 bits. That includes zero. Zero and it winds up being 256 options. Okay, it's actually 255, and then you've got zero, and that makes 256 in total. Okay, so you've got binary, you've got what's considered decimal, which is base 10. Okay, so this number right here, I just want you to kind of notice this. This number right here is a 65. Okay, and there's the decimal 65 that corresponds to the letter A. Now this system is called the ASCII, American Standard Code for Information Interchange. Okay, and that is a sort of universal code system that we map our keyboard into a computer a computer's logic with. Okay, and we know our keyboard, but there are many other characters in the world. So this small set of numbers here, 65 through 90, that's just the capital letters for uh, for our English alphabet. Okay, so you've got many other alphabets, many other sets of characters. They're not even, punctuation marks, the numbers, the digit system, all kinds of accent marks, everything out, all the Oriental characters in those languages are mapped to this ASCII system, and it's large. Okay, the only thing we're going to deal with, I'm going to ask you to deal with, or have you answer anything for on test, is this pretty much this set right here. Okay, just our letters. All right. So, um, one of the assignments for this week is for you to give me a binary greeting. I've got that set up. Let me see. Let me make sure I'm getting to this in the right place. Activities, discussions, and you can see that here, binary greeting. Here's my greeting. I don't think I did one. Let's see. Let's go to my other section right here. Let's see if I think I set this up so that you can see this. I'll have to put it in both of them. I really should. Okay, so we've got some in here. We've got some items in here, I think. Oh no, that's not it. That's an old one. It's a real old one. Well, let's just stick where I am here and use this. Okay, but you can post your greeting here. I believe I'm gonna oh, there it is right there. There's my greeting. Okay, Mr. James, welcome to class. And I left the E out of that, but it's in here. Okay, let me just fix that in fact. So I want to I want you to give me a greeting that includes your first name, your last name, and some word of greeting. Hello, welcome, howdy, uh, nice to meet you, um, whatever you want to say. Okay, aloha. But the whole thing needs to be at least 15 characters. Okay, so what I'm going to do is say to, there's actually a binary code that's in ASCII like this is for the space. In fact, it's right there. That's it right there. Okay, number 32. Okay, I'm not asking you to do that. You don't have to do that one. Just leave a blank. Leave a space between your 8-digit uh, bytes of sets of ones and zeros that correspond to the numbers that you're going to use for your message. Okay. Um, So that's what I'm looking for that. Just something pretty simple. Typically have this due on Sunday night. Okay, about 11:59. So try to get that done. Um, I don't think this is too hard. I don't think it's a too big of a thing to do. We'll do another binary activity next week. Hopefully, we'll all be back easily handling everything in class or online, and um, I can go over that with you and get you set up for that on Tuesday, I think, or Monday. So that's what's going on with that. Okay, now let me go into the rest of this a little bit more. Um, I do want to. That's pretty important. Okay, those corresponding sets of codes are pretty important to what we do with media. Okay, text. A lot of our media involves text. This is very integral to the RGB color system, and we'll talk about that. Okay, so let me make sure I've covered up to that point pretty well. Okay, this is a good page. I think it just in a larger form shows the corresponding sequence of codes and how they each mean the same thing. Okay, this is just a keyboard letter. This is a decimal number. This is a binary number. Those are the placeholders for binary. You can see that they double. They're just times two. Okay, it's a an exponent of two. It's a base two number system. Okay, 1, 2, 4, 8, 16, 32, 64, and 128. If you add all these up, if they were all ones, it would be 255. If you have all zeros, then that's of course zero, and that gives you the 256. Okay, so we'll talk about that in just a second in relation to color. This is a different, this in particular, these sets of 2 digits each in this case, for RGB color, red, green, and blue, we're using a different number system, which is a hexadecimal number system, base 16. And that's used to more concisely be able to convey our big color number system that we use. Everything from monitors, TVs, your watch, your car displays, anything electronic that you have, your tablets, your laptops, all that stuff, it's RGB color. Okay, now we do have other color models that are used today in kind of a large way. Broadcast TV is one of them. Uses a different color model, uses different components, winds up with a lot of the same type of thing, which is our color system, or just our eyes take it in and see it in their analog manner. But as far as digital and a discrete, storable mechanism to save color, it has to be done with some number system. So the only thing a computer can do is handle ones and zeros. That's all it does. And really, the only thing that it can do with that is add them. Um, uh, Multiplication is just a series of addition. Division is a variation of that series of addition that's used for multiplication. And of course, subtraction, we're basically adding negative numbers. So the computer is pretty simple. It only does certain things. It adds and it uses ones and zeros. Okay, so I do want to mention the color. We're gonna use this for a discussion assignment next week, but we'll get into that then. I will say we are going to talk about this, the color number system, and I think I'm probably going to save that for Tuesday, or Monday and Tuesday of next week, whichever class you're in, and uh, we'll go over that in more specific because that warrants that's a pretty big topic and that warrants its own. I think a little larger section of time. Okay, so these are examples of input devices that take analog data. Okay, now in this case with the scale, it doesn't really have a digital output. This is kind of there's a mechanical spring on here. You put some potatoes on here and you're going to weigh them. This is a produce scale in a grocery store, and uh, that whether depending on whether you put a few micrograms extra of potato on the scale, it might budge that red arrow a microscopic amount or not, or it might, if you took a little off, it might move it just a little bit. So that's really infinitely variable. Okay, same thing with the thermometer and the chemical inside there. As the heat expands that mercury, that could be measured in increasingly small amounts. Now we see these digits on here. Nobody really cares if it's 39.7 degrees outside. It's either 39 or 40 and nobody really cares. I mean, we know what that means, and that's all that really matters. Okay. But at some point the data we don't so at some point the data that we could capture but that we're not capturing doesn't really matter. Okay. All right. Processing, we turn an analog wave like this into a digital form. It goes into the computer as ones and zeros. It comes out something like this, a set of steps. Okay. All right. These are some file extensions that we might could save data into. I'm pretty big into file extensions, particularly because it has to do with what we deal with, which is creating and saving media projects, and you can't do it without these file extensions. So I'm kind of a stickler on file extensions. Okay, what ones are good for and what they're not good for. Okay, so let's keep going here. It's another little um, page about the binary number system. Okay, this has to do with storage capacities, and this is probably as detailed as I'm going to get about this as for what you need to know on a test. Okay, you need to know the major storage standard units that are available in like an external hard drive, for your RAM, for a flash drive, that kind of thing. Okay, so terabytes kind of is where we're at right now. I'm sure in a few years, eventually, we're going to get to petabytes and get bigger. Okay, but this is a trillion bytes right here. That's a lot of data. Okay, You do need to know that. One of the things that's kind of funny about this, okay, and that should have been an exponent right there, I think. Anyhow, one of the things that's a little bit funny about this, okay, when you get 1,000 bytes or 1,000 to the second power or 1,000 to the fourth power, whatever, that's bytes. That's not tens. That's not units of tens. So you really, the way those storage devices work, if you got a 1 kilobyte piece of storage, it's 1,024 bytes. Okay, that's 1,000 bytes. Okay, 1,000 times 8 bytes of data, and it gives you 1,024. It's not exactly 1,000. They always give you more. Okay, but the base the 8 bits for a binary piece of data does not correspond exactly to the decimal system, which we're so used to using. And honestly, the people that make these devices, they want it to be friendly to you as a consumer. And so they'll say, well, that's a 2 terabyte hard drive. Or hey, that's a 6 terabyte hard drive, or that's a 16 gigabyte or a 256 gigabyte flash drive or something like that. Okay. And they don't, that what they're telling you is something that they figure that you can comprehend. They don't, but they're really giving you a little bit more because the base 2 number system does not correspond exactly to the base 10 number system, and it just works out that way. Okay, you won't need to know that there are separate names for this, like a megabyte or a gigabyte or a gigabyte. Okay, I'm not going to ask you about that stuff. This is just the way I'm going to do it right here. But the thing that you need to know is which ones are bigger or smaller than which other ones. That's what you're going to need. You're going to need to know that a megabyte is smaller than a gigabyte, and a gigabyte's in between a megabyte and a terabyte, and a megabyte is 1,000,000 bytes. Those things you'll need to know. Okay, all right, pretty basic. This is a picture of an analog wave that's been captured and stored into a digital discrete stepped format like this. Okay, now the data that we lose is this data right here between the wave and the steps, the top of the steps. We've lost that data. We will never get that back when you make a recording or some type of recording, whether it's light and visual or sound and audio or whatever. Okay, we'll never can get that back, but it doesn't really matter because we have all of this down here and we can manipulate this. This is all in all these steps, and we can manipulate this, we can alter it, we can edit it, we can enhance it. Okay, this stuff that we can't capture, and as we get more capable of storing more and more data and better uh, programming and software that will capture that data, we capture more of it. And this area right in here gets smaller, but it's never going to close it totally. Okay. And it doesn't matter that we've lost this because we have all this. The trade-off is we can manipulate this. We can manipulate what we've stored. Okay. So that's a good thing to know. There's definitely a difference between analog and digital data. Okay. The wave is analog, the steps are digital. All right. These are input devices. This is what goes on with an input device. You uh, take an analog waveform, it goes through the device, it's converted into ones and zeros like this right here. Okay, the rest of it's thrown away. This is just a little chart here that explains what I just told you about this up here when we store a piece of data. Okay, this right here is the opposite process. This is output playback for a sound. Okay, it's output like this right here. Okay, so we take the ones and zeros, we put them back through the piece of software. The piece of software has an ability to talk with the output device, in this case, a speaker, and it will vibrate that software will vibrate that membrane when it plays back that file. It will vibrate those membranes in that speaker to reproduce the sound that it captured. It will reproduce it exactly, okay, but it cannot capture every little bit that we lost up here. So it's never really quite as good. Okay, now we can't tell the difference. We really can't tell. Um, And so it's not really that big a deal. Okay. But where this becomes a problem is as you save a file and you play it back, and if you re-record it and you play it back again, and you re-record it and you play it back again, or the same thing with an image file, you capture it from the original live world view and store it, and then you redisplay it back into analog form, because when it comes back out a speaker or back out through our monitor, those pieces of data, whether it's audio or visual or whatever, it's converted back to analog, so our body can comprehend it and take it in. Okay, it's converted back to analog. But if you do that multiple times, it degrades the quality of the of whatever the recording the file is. So you can redo that multiple times and begin to really degrade the quality. We don't really like to do that in general. Okay. All right. So talking about small pieces of data, this is a pixel, and um, typical red, green, and blue. In this case, they've got it ordered green first. Okay, and they're typically vertical. Sometimes they might be horizontal, but depending on the monitor or the display device. Okay, but this is typical. And if you look very closely, if you're when we're in class sometime, and I've got the projector on, if you walk up to it and look at it closely, you can actually see the squares, okay, that are the pixels. If you look real close at the projected screen, because it projects pretty largely, you can see the squares on there, especially in the white background area. Okay. And if you look real close, and this is hard to do, white is a special color in the RGB system. It means that all the red and all the green and all the blue are fully turned on. So they're flashing in their full colors. Okay. But if you look at a white pixel real close, you kind of can see these stripes, these red, green, and blue stripes in the pixels. Now that's a little bit hard to see, and it comes off looking like white when you just stand back and just look at the whole conglomeration of all these pixels, these white pixels. It just looks like white. Okay. Black's the opposite. Nothing is turned on in a black pixel. These would be black stripes. It's like looking through a hole in your monitor because there's nothing turned on. Okay. You can't see anything back through there. 8 bits are stored for each of these three colors. So we say typically that a pixel is the smallest addressable, uh, smallest piece of data in a visual image or a visual file, and that is true, except that really each one of those three stripes is actually the smallest addressable piece of data, because you can change the shade of green. You can turn this off a little bit or maybe a lot, and it changes this color. Okay. Red and green make yellow. If there is no blue and it's just red and green shining in full strength, you've got yellow. It will show up yellow. Okay. So of course, red and blue are going to make kind of a purpley or a violet color. Okay. So it's just something to know about with this digital media that we're dealing with. Okay. All right. We'll talk a little bit more about RGB next week because we're going to do a assignment with that. All right. So I've got to do a little bit more here, and then I'll wrap this up. If you have questions, you can email me. Um, or we can talk on Tuesday. I think what I'm going to do, since we'll talk. I'll send out an email about specifics for the assignments. Okay. All right. File compression. I'm pretty big into file compression, uh, especially file formats, because I think we really have to kind of know a little bit about what we're dealing with when we're saving and storing digital media. And in fact, I think I'm going to save from here, this the two big file compression, two categories or ways of looking at file compression. I'm going to save these: lossless and lossy. We'll talk about this next time, as well as these different file formats that we've got here, visual image file formats, and we'll talk about that next week. And get started on our next assignment, our next discussion. Actually, that one's not a discussion post, but we'll talk about it next week. Okay. All right. Good to share this with you. If you have questions, email me or we'll talk. I will send an email out after this. And if you still have questions, let's talk next week and in the first class and see what we can do. Okay. Thanks for being here. Good to share with you, and I look forward to next time.